Greetings and welcome to week 7 unit 1 on instruction for applying. In the last unit we understood some methods of instruction for critical thinking, and in this unit we will understand how to instruct for applying. The applying is in the context of revised Bloom's taxonomy, which has 6 cognitive processes, of which the lowest one is remember, then understanding, then applying. We have already looked at how to instruct for understanding. We will also look at the other cognitive processes, namely analyze and evaluate, in later units. In the revised Bloom's taxonomy, apply is carry out or use a procedure in a given situation. Okay, that's what we mean by the apply. You are carrying out or use a procedure in a given situation. It has 2 sub-processes: execute and implement. Execute, follow a known procedure or a set of steps accurately. That is, use tools, follow protocols. You have to use the protocol very strictly when you are executing. But as we stated earlier also, executing means what procedure to be used is already told to you. You are already supposed to know how to use that procedure, and you apply that procedure in a given situation. That is what it is. So, there is no ambiguity with regard to what procedure to be used. Whereas implement is the next level: put a method, model or technique into practice in a new or authentic context. What it means now, you are given a new context or a new problem in which you are not very clear what procedures to apply, whether the known procedures are applicable or not, whether you have to modify the procedure. None of that you are not clear, but you have to make a decision about it. That is, you must decide what procedure to apply, or if necessary do minor modifications to the procedure and justify them and then apply. So, that is what implement is. The instructional goals for apply in engineering programs is facilitate students to reliably performing tasks. Okay, that is execute, and using them to produce working solutions in real contexts. That is, you are taught or the students master certain procedures, and then they have a collection of these procedures already mastered, and from that you try to use that collection and pick tools from the procedures from that collection to solve a real world or authentic problem. That is what applying, the goal of applying is. Outcomes should emphasize fidelity to specifications, correctness, robustness, documentation and verification. Whatever you are producing, first of all it should meet the specification. Specification could be, let us say the solution should be, the value should be within 0.1% range, or it should be first correct, and then you should be able to document it, and you should be able to verify that whether you have done it correctly or not. So, these are the against which the learner will have to perform the tasks. Now we will look at execute. Let us look at some sample activities which you are very familiar. Solve a first order linear ODE, ordinary differential equation, by using an integrating factor. So what the task is given, dy by dx plus pxy equal to q of x. Compute the integrating factor mu of x equal to exponential integral p dx in that form, multiply through, integrate and produce general solution. Okay. And this procedure would have been explained to the students in the classroom by the teacher, and then you have to follow step by step. There is no deviation. That is, occasionally you may slightly differ, but you have to establish the correctness of the new procedure if you want to produce your own. Follows a step by step well defined algorithm. So the best thing is, first student follows the procedure given and masters that, and then he can explore any other alternative that he can generate. What do you deliver at the end of the task? A written solution showing mu of x and integrated expression, and finally y of x. You are solving for y of x, and you have to show what is the integrating factor and integrated expression and y of x. And how does one assess whether you have executed the task appropriately? Correct integrating factor, correct integration steps, clear algebraic simplification. So these are the goals against which the student has to understand the procedure and master the procedure. Another example, solve a linear system x dot, or you can say dx by dt equal to ax. A is a matrix, x is a variable, by diagonalization or matrix exponential. You want to solve for x. These are the two procedures available. Given 2 by 2 matrix A, find eigenvalues, eigenvectors, diagonalize if possible, compute solution for x of t equal to e raised to at into x at 0 time value. Okay. Non-linear algebra procedure sequence. It is known how to exactly perform this, and the student should be familiar with the sequence. And deliverable is eigenpairs, diagonalization of Jordan form, and x of t expression finally you have to give. That is the output you have to deliver. Assessment, correct eigenvalues, vectors, correct application of e raised to at including Jordan case. Okay. So when you present it that clearly, it is possible for student to focus on exactly what is to be done. You present, this is what you have to master, and I am sure student will be able to really focus for, there is no ambiguity in terms of what he requires to learn and perform. Another sample activity, execute, flash firmware and run a provided test script. Task is program the supplied microcontroller, image, connect sensors, and run the test harness that exercises I/O and report pass fail. This is something like in a laboratory type of thing where you are giving an execute task. Uses an established sequence which is taught earlier: flash, configure, run tests. Deliverables: console test log showing all tests passed. That's what has to be shown. Assessment: successful test run, correct serial log outputs, short comment on any failure. Okay. And tip: give students a known good image to compare logs against. So that is one example of execute. The first two are mathematics type theory type of questions, and the third one is more like in a laboratory. And if you want to look at samples for implement, these will be a little more elaborate and a bit open-ended, and more decisions have to be made by the student. IoT sensor node deployment. In an IoT network, you are you are creating one node. Task is implement a battery-powered temperature humidity node using MCU, sensor, and a LoRaWAN, I am not familiar with that, radio, integrate with cloud backend and demonstrate reliable 7-day reporting. That's a task reasonably. It can be incorporated as an experiment in the lab in an IoT course. Students adopt hardware, software patterns to a real deployment, that is power management, comms, retries and so on. Deliverable, a PCB or a breadboard, firmware, cloud ingestion dashboard, energy budget log. These are the outputs they have to produce, and then assessment is functionality, uptime, mean time between failures, energy per report, documentation. And another sample activity for implement, prototype actuator for a pick and place arm. You're prototyping, it's a laboratory work. Implement a lightweight actuator and control linkage that meets prescribed speed, precision to pick components. Use kinematics and actuator selection methods in a real subsystem with constraints, mass and cost. Deliverable, CAD assembled prototype, test report showing repeatability and accuracy. Because if you have some robotics lab like this, you will have all the mechanisms available, and the student has to choose and then assemble them to perform this task. Assessment, positional error, cycle time, robustness, manufacturability notes. You can create variations to this task, trade accuracy versus speed, add sensors for closed loop control. So you can modify the task in several ways to make the problem more interesting or more complex or less complex. Now a civil engineering example, stormwater management for a small site. Task, implement a detention or retention system design, grading, swales, detention basin, permeable paving, use any of those methods that keeps 10-year storm runoff under threshold. Apply hydrologic models and local codes to an actual site plan. There will be local codes also available in each region for stormwater management. Deliverables, site drawings, calculations, cost estimate, maintenance plan. All of them will have to be given, and for each one of those deliverable, you may have to use a different procedure, or maybe an option of methods are available, and you have to choose, justify your selection, and then produce the output. That's what constitutes an implement. Assessment, compliance with regulations, hydraulic performance, constructability. Can that be constructed? Can you justify whatever structure that you want to create? Is it constructible? Okay. Deploy, another example, deploy a fault tolerant microservice. Task is implement a microservice using container orchestration with CI/CD, auto-scaling and graceful degradation under load. Apply software architecture patterns and deployment procedures in a production-like environment. Deliverables are code repo, deployment manifest, load test report, runbook. Assessment is availability under fault injection, latency percentile targets, rollback capability. Now these are some samples that are given. Depending on the course, the teacher will have to design a whole bunch of exercises or apply activity both in execute mode as well as implementation mode for the students to really experience the entire subject. Okay, how do you instruct now for execute and for implement? Let us look at that. As far as instruction for execute, the goal is procedural fluency. Can I perform this procedure without any hesitation, or you know exactly how to do it precisely that particular task. How does the teacher prepare students for that? Modeling and worked examples. Instructor demonstrates step-by-step procedures. For example, lab setup, wiring test sequence, unit test writing and so on, with narrated reasons for each step. Why are you doing this? If that is explained, it will stay better with the students. And then guided practice. Scaffolded labs where students follow checklists, complete discrete steps with immediate feedback from teaching assistants or auto graders if you have, if you have any software tool. And distributed practice, frequent short low stakes exercises, run the simulation report X to build automaticity. One of the issues with learning is, if something is not used for some time, the way our brain works or the way our memory happens is, if you don't use certain procedure for some time, then those synaptic connections starts becoming kind of light and then vague, and then you are not clear about some of the details. So one method is to frequent short low stakes exercises. If you consider that procedure is important to be remembered, then you keep doing that. If you are repeating that exercise in different contexts repeatedly, it is likely to stay with the student for a longer period. Micro skills training and focus on individual techniques. That is micro skills, like using oscilloscope probes safely. Okay, in the lab they can be trained. You have to exactly do this. That will be easier for a student to pick up that particular thing if he is taught properly. If he has to explore to find out how it is to be done, like oscilloscope probe, then there might be some errors in the way he is doing it. You should not blame him for that. So it is better to focus on identify all the micro skills that are required and train them, make sure there is what you call procedural fluency in that. Okay. And assessment here will be direct assessment. Student performs something, you are immediately saying whether it is right or wrong. That's it. So it is a direct assessment. Whereas instruction for implement, there can be several ways. Implement asks students to put methods, models or techniques into practice in new or authentic contexts. Adopt procedures, integrate components, make trade-offs and produce working documented solutions. Okay. Instruction should prioritize authentic tasks, supported practice and feedback that emphasizes transfer, robustness, and engineering judgment. So, the instruction should prioritize these steps actually. Now, some of the instructional strategies for it, it is not one. One is project based and design based learning. This has been elaborated in the previous units, and they certainly will test all the steps in what do you call in the instruction for implement. So you don't have to separately train, separate it out, implement instruction separately. If you have a component of project based or even problem based learning, if you have one unit of that, that will address the of apply. And the only thing that is required is you have to make sure that the rubrics that you are going to use for evaluating are appropriately designed and they are communicated to the student. Then the other one is cognitive apprenticeship, modeling plus coaching. It is like true apprenticeship. Instructor or teaching assistant models how to adopt a method in context. That is, he thinks aloud and then coaches the students through guided practice, makes tacit professional reasoning visible. So keep on going through the steps, keep talking about it and actually perform the tasks, and through that, and you can also grade it. That is, you perform certain tasks and make sure the student has understood and then go to the next stage and so on like that. It can be, you can also scaffold those things, so it is easier for all students to practice that. So scaffolded authentic tasks, that is progressive fading. Start with the partially completed or highly scaffolded implementations. Gradually remove the scaffolds as competence rises and supports transfer without overwhelming novices. The scaffolding is an idea. That decision has to be made depending on the kind of students that you have or the time you have. As the time to pick up and master and move to quickly, that means you are creating multiple steps before going to your goal, before achieving the goal. The other one is industry style iterative development. Require time boxed iterations. Design, implement, test, reflect. You set timings for that and you exactly perform that. And by doing this kind of thing, this iteration mirrors engineering practice and creates a natural checkpoints for feedback. So if you are able to, let's say even 2 or 3 cases, if you are able to implement that, you are really preparing your students for the industry. More than subject, these are the practices that you require. That in industry, people put timelines like this for design, implement, test, reflect, and then if student is able to plan and perform like this, he is ready for industry. Okay, integrated assessment of non-functional requirement. Every product has non-functional requirement. What are the normal non-functional requirement? For example, robustness, maintainability, safety, performance, and documentation. And here, these are not functional specifications. These are non-functional ones, which are equally important whenever you think of a product. You cannot just say it works and give them a bunch of wires and distributed over your lab bench. That doesn't constitute a product. That is, you have not attempted any of the non-functional specifications. For example, is that product that you are, whatever that you are producing, is it maintainable or is it safe? Has it been adequately documented? These are all the non-functional requirements. So, if you give a integrated assessment of non-functional requirements, then you are really preparing him for a product, your project itself. If a project consists of a product to be produced, then he is ready. If this can be incorporated in one of the courses, it will prepare the student well. Then cross-disciplinary and system thinking tasks require students to integrate multiple components, hardware plus software, control plus mechanical, and that is like what do you call cross-disciplinary type of thing, and strengthens ability to implement in complex contexts. Depend. For example, if you have a undergraduate program in robotics or automated manufacturing, some of those things, they are across the disciplines, electronics, electrical and mechanical all put together. So, you can have a cross-disciplinary projects like that. Further, instruction for implement, use of authentic tools and workflows. Require version control, issue tracking and continuous integration, CAD/CAM pipelines, hardware bring up procedures or deployment scripts, prepare students for real engineering practice. If you are all the tools that are required to perform a task or a project, if all the tools are the student is required to integrate all of them, that will make a good practice, good implementation task. Then you can also use peer review, peer team implementation, which is self-explanatory, and then simulated and field deployments. Use realistic simulators, hardware in the loop or small field deployments to test implementation and under realistic variability and constraints. This of course requires a lot more infrastructure. It may not be possible all the time, but this is a good implementation or instruction for good implementation. It may not work out. If your lab is well provided, then you can try some of these things. The hardware in the loop is an expensive process. Okay. So that is how you instruct for execute and implement of apply. And as you can see, these you don't have to look at it in isolation. It can be incorporated practically into many of the engineering courses, and when you are addressing in a course any of these, then you can follow these instructional methods for that to be effective. And in the next unit we will look at how to instruct for analyze cognitive process of revised Bloom's taxonomy. And thank you for your attention.